we are going to rank again molecules in order of acidity using the tool ARIO. We're doing that analysis. Now this time, let's see, before I give you a series in another video that included this acid and phenol also. And now I'm going to include in the series something else. We're going to do these, and we're going to do now, yes, compound. And previously we said that carboxylic acids are stronger acids because here we see that the conjugate base, here, two things, charges on an oxygen, and also I can do resonance. So that was the strongest acid here. And in fact, pKa of acetic acid is 4.7. Now, when I take that proton out, we remove that one in phenol, I form the following conjugate base. And here is O negative because I have 3 lone pairs after removing. That also charges on an oxygen and I have resonance, but the contribution of the resonance structures is not wrong arrow. But good that I did a mistake. I'm going to show you why if we cannot expand the octet. Wrong arrow here. So I'm going to move those electrons over here, make a double bond, and then this electrons here. All right. So what I'm saying is that the resonance structure here are going to place a negative charge on carbons. So it does not contribute as much as the two resonance structures that I can draw here. Now pKa of phenol is about 10. Now here I have two more molecules, acetone, and let's do, here all of the hydrogens are attached to carbon, but I'm going to remove one of them. So remember, this is a CH3, this is a CH3. So removing one of the hydrogens here, I am going to have the following conjugate base. This is going to have a pair of electrons here, so it is on a carbon. Now I am removing hydrogens here. But first, let's see, this lone pair is allylic to this double bond, so I can do resonance here. I'm going to move those electrons. And now this time, and let's see, I'm going to have to do those on the top. So the resonance structure here is placing charges on the oxygen, and I have that. And that is a CH2. Just to remind you, that was a CH3. After removing the hydrogen, that became a CH2, right? And let's throw it off. So those are my resonance structure. So it does have resonance, but here charge on a carbon, charge on an oxygen, right? So that will contribute more to the hybrid. But this is different to this example in which the two resonance structures have the charge on an oxygen. So it will be less acidic. And in fact, these compounds have a pKa, so ketones, for example, pKa's are around 20, 19, 20, something like that. And I want you to look at this molecule. We're going to contrast this two using same tools. So I am drawing now the structures of determining in this molecule what hydrogens are more acidic. And because I need more room, I am going through probably, well, let's do it on top. So let's say that I have here one type of hydrogen, hydrogen A, same here. And I also have hydrogens here, but I'm going to draw just one hydrogen B. We have 3, and those 3 here are the same. So I am going to draw 2 conjugate bases. Removing hydrogens in A will lead to the following. I'm removing one of these. If I remove that, I create that. But that conjugate base is stabilized by resonance. I can do that. And in doing so, I am creating the following resonance structure. Double bond here. Right, well, it is too high, probably you won't be able to see it in my video. Okay, by doing that, let's draw the resonance. And I keep having too much stuff here. All right. So I am drawing the resonance structure that I did, and that is, still have this, is a carbonyl group. In doing that, I'm creating a double bond, and now I have negative charge on an oxygen. But you probably, you can see here that those pair of electrons, I did move to that carbonyl, but I could have done it to the other side. And if I do it over here, I will move now and create charges here. So I have another resonance structure. And in that case, well, I'm going to do it then on the top again. Hoping that I have enough room here. And probably not. Probably not. So what do I do? Oh, well, I'm removing this. So you guys, because I want to compare the different structures, I don't want to erase them all. That's my whole idea here, is that we compare the different molecules, right? So when I do the movement indicated by the blue arrows, I'm going to do this arrow as if it was a resonance structure arrow. I am going to create the following anion. Next, notice now I have all these resonance structures for the compound that is here. I created the conjugate base for removing protons A, but that has 3 resonance structures. Well, they contribute a lot to the resonance hybrid, and in fact help stabilize this anion so much that the pKa, this is much stronger. These hydrogens are more acidic than these ones that can also be stabilized to one side, let's say. So here, pKa of this compound is around 9. So notice much more acidic than this one. And the effect that we are analyzing here is resonance. So notice here, removing 1 hydrogen, I had this anion, which has 1 resonance structure. Removing hydrogens A here in this compound gave this an ion that has these 3 resonance structures, so more stabilized. And finally, if we have to compare now removing in the molecule on here that I drew, we have labeled 2 different types of hydrogen. And what I want you to see that if you remove one of these, it's similar to that case. So removing one of the other hydrogens on the end. If I did that, you're going to create this. And here you can only draw resonance structure to one side. So in this molecule, hydrogen A are more acidic and they are stabilized by resonance. We'll do more later.